There's a fault line at the bottom of the world that most people have never heard of. It sits between South America and Antarctica in the remote Scotia Sea, far from any city, any coast, any shipping lane. Almost nobody lives near it. Almost nobody talks about it. And that obscurity is exactly why it keeps surprising people. On August 22nd, 2026, a magnitude 6.2 earthquake struck this fault, the South Scotia Ridge. It was the largest earthquake globally in the past 24 hours. It was shallow, only about 10 to 11.5 kilometers deep. It was pure strike-slip motion, the ground sliding horizontally past itself. And it happened just 67 kilometers from the epicenter of a magnitude 7.8 earthquake that tore the same fault apart in 2013. The 2013 earthquake did not start as a 7.8. It started as a 6.1, then 4 days later, a 6.8 hit. And then 30 hours after that, the fault exploded with a 7.8 that sent seismic waves racing around the planet. Now look at what happened yesterday. A magnitude 5.7 hit first. Then 7 hours and 42 minutes later, a magnitude 6.2 struck the same region. The escalation pattern, the location, the fault type, the depth, everything is pointing in the same direction. By the end of this video, you'll understand why this remote fault line matters, why scientists are watching it closely, and what the next few days could reveal. Let's start with what actually happened. A strong and shallow earthquake registered by the USGS as magnitude 6.2 hit the Scotia Sea at CU 822 UTC here on August 22nd, 2026. The USGS reported a depth of 10 kilometers, or about 6.2 miles. The EMSC, the European Seismic Monitoring Agency, reported the same magnitude and depth independently. When two independent agencies confirm the same numbers, that is a strong signal that the data is reliable. The epicenter coordinates are 60.379 degrees south, 47.605 degrees west. When seismologists see 10 kilometers as an initial depth assignment, it typically means the earthquake is shallow and the exact depth is being refined. The reviewed moment tensor, the scientific reconstruction of exactly how the ground moved, gave a depth of about 11.5 kilometers. That is still extraordinarily shallow. And shallow is the word that matters most in this story because shallow strike-slip earthquakes on this specific fault system are exactly the type that have produced the largest and most violent seismic events in the Southern Ocean in living memory. The epicenter was located 1,230 kilometers east-southeast of Tolhuin in Tierra del Fuego, Argentina. It was 1,368 kilometers east-southeast of Ushuaia, the world's southernmost city. And it was just 60 kilometers from the epicenter of the 2013 magnitude 7.8 earthquake. The location is critical. The epicenter sits in a point of the ocean that lies between the bottom tip of South America and the frozen continent of Antarctica. There's almost nothing out there, just ocean, ice, remote islands, and one of the most geologically violent tectonic boundaries on the face of the Earth. The moment tensor analysis of the 6.2 shows fault planes that are nearly perfectly vertical, dip angles in the high 80-degree range. The rake values, which describe the direction of slip motion along the fault plane, are extremely close to pure horizontal. The crust on one side of the fault slid sideways past the crust on the other side, pure left lateral strike-slip motion. This is textbook South Scotia Ridge behavior. This is mechanically identical to the 2003 magnitude 7.6. This is mechanically identical to the 2013 magnitude 7.8. When you see the same fault geometry repeated across multiple major earthquakes on the same boundary, you are looking at a pattern, not a coincidence. The fault surface is essentially straight up and down, nearly perpendicular to the Earth's surface. The two sides of the fault are not pushing into each other or pulling apart. They are grinding past each other horizontally. This kind of fault motion is called transform motion. It is the same type of motion that occurs on the San Andreas Fault in California, but here it is happening at the bottom of the world, on a boundary that is far less understood because it is so remote. The depth of this earthquake is critical. Shallow earthquakes are more dangerous because they release their energy closer to the surface. The shaking is more intense. The ground motion is more violent. A deep earthquake might be felt over a wider area, but the shaking at the surface is often less severe. A shallow earthquake concentrates its energy in a smaller area with much higher intensity. The fact that this earthquake occurred at such a shallow depth means that if it had happened near a populated area, the damage could have been significant. Fortunately, it happened in one of the most remote places on Earth. The 2013 earthquake sequence along the South Scotia Ridge Transform initiated with a magnitude 6.1 event on November 13th and a magnitude 6.8 event on November 16th as foreshocks, located roughly 50 kilometers west of the main shock. Then on November 17th, the main shock ruptured with a magnitude 7.8. I'll read those numbers again: 6.1, then 6.8, then 7.8. The 2013 main shock did not arrive without warning. It was preceded by two foreshocks over 4 days that escalated in magnitude before the main fault rupture unleashed energy on a scale that shook seismographs worldwide. The 2013 magnitude 7.8 rupture spread primarily eastward at roughly 2.5 kilometers per second, with a total rupture duration of about 120 seconds. Aftershocks extended roughly 250 kilometers eastward. 120 seconds of rupturing, 2 full minutes of the ocean floor tearing apart. The rupture front racing eastward at 2.5 kilometers per second across a fault zone that ultimately generated aftershocks spread over 250 kilometers. The physical scale of what that 7.8 did to this plate boundary was enormous. To put that in perspective, the fault rupture length of the 2013 earthquake was longer than the distance between London and Paris. The energy released was equivalent to hundreds of atomic bombs. Now go back even further. The 2003 Scotia Sea earthquake of magnitude 7.6 demonstrated the potential for large seismic events within the system. This earthquake occurred along the South Scotia Ridge and was felt across much of the southern Atlantic region. So within a span of just 10 years, the same boundary produced a magnitude 7.6 in 2003 and a magnitude 7.8 in 2013. 2 major earthquakes approaching magnitude 8 on the same fault 10 years apart. Now compare that 2013 opening sequence to what just happened yesterday. The 2013 sequence started with a 6.1, then escalated to a 6.8, then exploded to a 7.8. Yesterday's sequence started with a 5.7 and escalated to a 6.2 just under 8 hours later. The epicenter of August 22nd, 6.2, is only 67 kilometers from the 2013 magnitude 7.8 epicenter. The fault motion in yesterday's earthquake is pure left lateral strike slip. The exact same motion that characterizes every large historical earthquake on this boundary. The depth is shallow, matching the 2013 events, and the sequence shows the same escalating 2 earthquake pattern that preceded the 2013 catastrophe. Fault sections that have been locked since their last rupture have had 13 years to accumulate fresh elastic strain from the continuous plate motion. At 11 millimeters per year of plate movement, 13 years represents roughly 143 millimeters, about 5.6 inches of total plate motion that either happened through gradual creep or was stored as locked elastic strain. If that section near yesterday's earthquake epicenter is partially locked, it has had over a decade to reload. The fault is not sitting idle, it is accumulating energy. Let us talk about what fault this earthquake actually happened on. The South Scotia Ridge is the plate boundary between the Scotia Plate and the Antarctic Plate. It runs roughly east to west across the southern Scotia Sea. The South Scotia Ridge is a left lateral transform boundary that is sliding at a rate of roughly 11 millimeters per year. Left lateral means that if you are standing on one side of this fault and looking across it, the ground on the opposite side appears to be moving to your left. This is pure horizontal sliding motion. The 2 sides of this boundary are not colliding into each other and building mountains. They are not pulling apart and creating new ocean crust. They are grinding past each other sideways at 11 millimeters per year, year after year, decade after decade, century after century. 11 millimeters per year sounds harmless, less than half an inch per year. But here's the physics that makes slow fault motion terrifying. Every millimeter of plate movement that does not happen smoothly through continuous creep is instead stored as elastic energy in the crust. The fault locks. The plates keep trying to move. Stress builds and builds and builds until one day the locked section can no longer hold the accumulated strain, and it releases everything at once. The energy that builds up over years and decades in a locked segment of plate boundary is released in seconds. The instantaneous release of decades of stored elastic energy is what an earthquake is. The northern edge of the western South Scotia Ridge is marked by a subvertical left lateral master fault. The plate boundary is segmented by a series of release zones that have favored the fragmentation and dispersion of crustal blocks across the region. Segmented means this is not one simple clean fault running in a straight line. It is a series of connected fault sections with bends, steps, and structural complexity that makes predicting exactly where and when energy releases very difficult. But that same complexity is also what makes the historical record here so important for understanding what is happening right now. Such sideways moving events can destabilize adjacent segments of a fault in a sort of domino effect. The British Antarctic Survey published that assessment based on direct observation of what happens to this specific fault boundary after major strike slip events. When one section releases its stored energy, the stress does not disappear. It redistributes. Some of it goes into the surrounding crust as aftershocks, but some of it transfers to adjacent fault sections that were already under stress, effectively pushing them closer to their own breaking point. This is called stress transfer. And on a segmented fault system like the South Scotia Ridge, stress transfer from one section to its neighboring sections is a real mechanism that scientists have documented here specifically. The Scotia Plate formed when the Drake Passage opened, separating South America and Antarctica. It sits directly between these two enormous plates, with its boundaries wrapping from Tierra del Fuego around the Scotia Sea and toward the South Sandwich Arc. At the western end of the South Scotia Ridge, near the Drake Passage, the fault system transitions and connects to transform faults running through Tierra del Fuego and the southern tip of South America. The Magallanes-Faguenot fault system in Tierra del Fuego is part of the same broad left lateral plate boundary accommodating sinistral motion between the Scotia and South American plates. It has its own history of major historical earthquakes, including a magnitude 7.8 in 1949. Let us talk about what is physically near the epicenter of yesterday's earthquake, because the geography matters for understanding the human dimension of the story. The Argentine research base, or Station, perched on Laurie Island since 1903, holds the distinction of being Antarctica's longest-running research facility. It maintains an unbroken scientific presence with around 14 people weathering the winter months and up to 45 researchers during peak summer operations. That research station has been continuously occupied for 123 years. It sits on Laurie Island, one of the four main South Orkney Islands. And the western edge of that island group is roughly 50 kilometers from yesterday's magnitude 6.2 epicenter. Seney Research Station on Seney Island serves as Britain's window into Antarctic life. The station's climate is characterized by low temperatures, gales, and coastal weather conditions. Researchers have been collecting microclimate records for over 25 years. Seney Island itself spans 6.5 kilometers in length and less than 5 kilometers in width, with the research station housing typically around 5 to 10 scientists during the summer season. These are real human beings conducting real scientific work less than 100 miles from where a magnitude 6.2 earthquake just struck. Not a large population, not a city, but researchers who have chosen to work in one of the most extreme environments on the planet and who are now sitting in the aftershock zone of a significant shallow earthquake on a fault that has produced near magnitude 8 events. The South Orkney Islands have a long history of seismic activity. The region has experienced numerous earthquakes of varying magnitudes over the years. The proximity of these research stations to active fault lines means that scientists working there are constantly aware of the geological forces at play beneath their feet. There are 3 things that will tell the story of whether this stays a moderate sequence or escalates towards something historically significant. The first is the spatial migration of aftershocks. Aftershocks from yesterday's 6.2 that stay tightly clustered around the initial epicenter suggest a contained rupture zone releasing local stress. But aftershocks that spread east or west along the South Scotia Ridge boundary indicate that the rupture redistributed stress to adjacent fault sections, and those sections are now responding. The direction and extent of any aftershock migration over the next 48 to 72 hours is the single most important indicator of what this sequence may become. The second thing to watch is the focal mechanisms of any subsequent events. Every earthquake that follows the initial sequence can be analyzed for its fault motion. If follow-on events show the same nearly vertical strike-slip mechanism seen in yesterday's 6.2, that confirms the sequence is confined to the South Scotia Ridge Transform system and behaving consistently with its established seismic character. That is the expected result. But if any events show different fault geometries, it could indicate that the stress field is more complicated or that secondary structures near the South Orkney microcontinent are being activated. The third and most critical thing to watch is whether any future events in this sequence begin migrating toward the sections of the South Scotia Ridge that ruptured in 2003 and 2013. The 2013 main shock hypocenter was roughly 50 kilometers east of its foreshocks and aftershocks, extended 250 kilometers further eastward. Those sections of the fault absorbed enormous slip in 2013 and have been reloading since. Whether the section immediately adjacent to them, where yesterday's earthquake struck, transfers significant stress in their direction is the key question for anyone monitoring this boundary over the coming days. The first 24 to 72 hours after a major earthquake are critical for understanding whether the sequence will escalate or subside. Scientists will be watching the data stream in real time, looking for any signs that the fault is continuing to rupture. Every aftershock is a data point that helps build a picture of what the fault is doing. Here is what you need to carry away from everything you have just heard. Yesterday's magnitude 6.2 is the largest earthquake globally in the past 24 hours, confirmed by multiple independent seismic agencies, including the USGS and EMSC. It struck at 10 kilometers depth on a fault that has produced magnitude 7.6 and magnitude 7.8 events within the last 23 years. It was preceded by a magnitude 5.7 just under 8 hours earlier, mirroring the escalating foreshock sequence that preceded the 2013 catastrophic rupture. Its epicenter is 67 kilometers from where the 2013 7.8 originated. Its fault motion is pure left lateral strike slip, mechanically identical to every prior major event on this boundary, and it is happening 13 years after the last major rupture, more than long enough for significant elastic strain to have reaccumulated in the surrounding fault sections. The fault has had time to reload. According to the USGS, there are no land-based observations within the Scotia Plate to measure plate motion. All reported plate motions are derived from remote earthquake recordings. That sentence is critically important. We know what this boundary is doing because of the earthquakes it produces. There are no GPS stations sitting on the Scotia Plate telling us how fast stress is building. There are no strain gauges. The only way we can measure what this boundary is doing is by watching the earthquakes it generates. None of this means a 7.8 is coming tomorrow. Let that be completely clear. Nobody can tell you that. Earthquake science does not work as a reliable short-term prediction tool, and anyone who tells you otherwise is overstating what the science can actually deliver. But what the historical record, the fault mechanics, the seismic behavior, and the location of yesterday's earthquakes altogether tell you is that this is not a random isolated tremor in a geologically quiet place. This is a very specific type of earthquake on a very specific fault, in the same section of that fault that has produced some of the most powerful strike-slip earthquakes in the southern hemisphere in the modern era. That combination demands serious attention. The South Scotia Ridge is one of the most seismically powerful and least monitored tectonic boundaries on the planet. It sits between two enormous plates in the most remote ocean on Earth. Almost nobody lives near it. Almost nobody talks about it. And that obscurity is exactly why it keeps surprising people when it does what its history says it can do. Within just 10 years, the same boundary produced a magnitude 7.6 in 2003 and a magnitude 7.8 in 2013. Now in 2026, 13 years after the last major rupture, the boundary is producing an escalating 2 earthquake sequence in the same zone where both of those previous events originated. The pattern is clear. The fault is active. The stress is building. The South Scotia Ridge has earned the right to be taken seriously. Yesterday, it reminded the planet that it is still there. It is still moving. And it still has plenty of stored energy left. The aftershock sequence from yesterday's events is developing. Scientists are watching the data stream in. The question of whether the August 22nd, 2026 sequence stops here or becomes the opening chapter of something larger will be answered by the data over the coming days. The South Scotia Ridge is not finished. It never really is. If this helped you understand what's happening beneath the remote southern Atlantic, hit that like button, because it helps more people find real, honest coverage instead of the exaggerated stuff. Subscribe so you don't miss updates on this developing story. Drop a comment. Did you hear about this earthquake before watching this video? And if this helped you, check out my video on the San Andreas fault swarm. Stay informed, stay prepared. I'll see you in the next one.